This is 7.5.3 magnetic flux and flux linkage. So we'll do a quick recap on what we mean by flux. So in any force field, the strength of the field is described by how dense the field lines are. So up to this point, we've been calling them field lines. Now in gravitational fields, when we describe the strength of the field, we say magnetic flux density. So how dense this thing called flux is. So when we're talking about flux, we're just talking about field lines, how dense field lines are. Now that's flux density. But if I just say the word flux, it's just talking about field lines. Yeah? Now, there's a caveat here, is that field lines are a visual description of a field. But in reality, it's not like these lines and arrows actually exist. Rather, there's some field that exists in that space, some phenomenon. And that phenomenon can have a different amount of this stuff that we call field passing through it. So it's just a way of thinking about it. So when I say flux, we're not actually saying there's one field line or two field lines. Because what each field line represents when you draw it is arbitrary. I could draw a field line that's got 3 lines, maybe like 5 centimeters apart. And in my drawing, that could represent a strong field. And someone else's drawing, that could represent a very weak field. Yeah? So it's not like these lines actually exist, but rather we draw them as a visual depiction to understand what's going on. Anyway, so we'll draw a magnetic field. Again, I'm going to do a uniform field. And these field lines, or the flux, will be pointing down. And then I'm going to draw a coil of wire within that field. And draw the coil of wire coiled as a square rather than a circle. So here we have some coil. Now for simplicity's sake, I'm not drawing 2 wires coming off the coil connecting to a circuit. We just assume it's there, but we're not drawing it, just to simplify our diagram. And the coil can be n turns, can be n number of turns. So this basically just means how many times it's coiled. Now to have a coil, the minimum number of coils is 1. You can make 1 coil, that's 1 loop. Then you can do a second loop, and a third loop, and a fourth loop, etc. So what I've drawn 1 loop only. But we can draw multiple of these. This coil encompasses some area. We label that as A. Now when we're looking at coils, we use something called an indicator. An indicator is an imaginary arrow that extends from the plane of that area that we've drawn. So kind of like when you're doing reflection and refraction, we draw an imaginary normal line. So we're doing the same thing, we're drawing an imaginary line. So if we were to look from the side, so I'm going to draw the same diagram, but we're going to look at it from the side. Our coil just appears to be a flat line because we're looking at it dead from the side, so we can't actually see it going into the paper. And our field lines again are going down, that's B. And our indicator is just this imaginary arrow. It's an imaginary line.
What line?
You'll see later on.
Is it always like in the opposite direction of the vehicle?
the indicator is always at right angles to the area. I could have drawn it pointing down. I could have drawn it pointing up. As long as it's perpendicular to the plane of the area. Yeah? Now, the total flux that passes through that area, well, that's going to be the flux density, how tightly packed the flux is, multiplied by the area encompassed by that coil. So if I have a flux density, which is how tightly packed the flux lines are, and I multiply it by the area encompassed by the coil, that tells you how much flux passes through the coil. So for 1 turn of wire, the total flux, phi, is equal to B times by A. Put a box around that. Phi is the magnetic flux, and it's measured in units called Webers, WB. And B, as you know from before, is the magnetic flux density. And that has units Tesla, or the alternative units is if the flux is Webers, and then flux density is flux divided by area, then the flux density can also be measured in Webers per meter squared. Now, for a coil of N turns, so that would basically look something like this. Right? So there's N number of turns in this coil. Each coil, so each loop, has that flux going through it. Because all the coils are grouped together, the total flux passing through the entirety of that coil, of those coils, is the number of coils times by the flux for one coil. Now they all have the same area, so every single one of them has phi equal to BA. And because there's N times the number of coils, then the total flux going through every single coil added together is NBA, or BAN. So now we write that as N phi equals to BAN. And N phi is called the flux linkage. It's called the flux linkage because now we've got flux through 1 coil, 2 coils, 3 coils, 4 coils, 5 coils, and we've linked them all together. So each one has got phi, and because there's N times the amount of them, the flux linkage is N phi, which is BAN. Now this is only true this is only true in this position, which is the same position we had before. So we've got our flux, and then what I'll do is I'll draw our N number of coils like this from the side. That's our N number of coils.
Do the coils have to be stacked?
Well, yeah.
But would it, if they're spread out, wouldn't each coil have the same force applied to it?
If the coils were spread out, then each coil progressively gets a larger and larger area. And so each successive coil then ends up having a larger flux going through it.
What would you mean by they getting a larger area?
Well, you said that the coils spread out. So if each coil spreads out over the next one,
Oh yeah, yeah.
then the more N turns you put, the bigger the area that the coils end up taking up.
How about
So the very last coil that you wrap around will have a greater area than the first coil that's been wrapped.
if we don't treat them as coils, we treat them as cards, right? And they're not touching. They're just cards that are just next to each other. So like one coil could be here and like a completely individual other coil could be there.
These coils are made of one length of wire,
I'm talking two separate wires.
but then they've got nothing to do with each other.
But then with the formula still work.
No, because they've got nothing to do with each other. Because each one is a separate system.
Yeah,
So they're not together. So, sometimes though, we can have more complicated scenarios. So the general formula is N phi equals to ban cos theta. So we can draw what that looks like. So again, I'll draw the field lines and label that as B. And we'll draw our coils. So we'll draw our coils. Again, n number of coils. It could be one, it could be multiple. And I'm going to purposely draw the indicator very, very close. Or in fact, I'm going to draw it as touching one of the field lines. So I'm going to draw it touching the middle field line. And again, we're going to draw it as being at right angles to the plane of that of the area of the coil. And the indicator forms some angle, theta, between itself and the field line. Now, looking at that, we get a maximum value for the flux or flux linkage when the angle is equal to 0 degrees. And we get 0 flux when theta is equal to 90 degrees. You can do it through Fleming's left-hand rule, but another way is you just look at how much flux is passing through the coil of wire. Now, if I have it at 0 degrees, then you can see the original diagram I drew above. All of the flux passes through the coil. Once you start to rotate it, less and less flux passes through the coil up until, let's rotate it a little bit more. So I'm going to rotate it now fully 90 degrees. So here's our coils here. Again, we do an n number of coils. And I'll draw the indicator. And that now forms 90 degrees with the field lines. Well, now if you look at that, how many field lines are passing through the area of that coil? None. Because those coils now are aligned in such a way that the field lines run parallel along the plane of the area rather than passing through it. So at that point, flux is 0 because no field lines goes through that area. We could do an example. So a coil has area 0.20 meters squared and 50 turns. It is in a B field of 400 millitesla. Calculate A, the maximum flux linkage, and B, flux linkage when coil is rotated by 30 degrees. You can pause the video here to calculate the answers and then play the video when you're ready to see the solutions. Okay, for part A, we simply want to find the flux linkage. So we do Nϕ equals to BAN. Flux density is 400 millitesla, so that's 400 times 10 to the minus 3. The area was 0.20 meters squared, so times by 0.20. And there were 50 turns of wire, so multiplied by 50. Then you simply put that into a calculator, and you should get about 4 Webers. Then for part B, because it's now rotated, we now have an angle. So it's Nϕ equals to BAN cos theta. Now we've already worked out BAN, which was 4 from the previous question. So we only need to put the new angle that it's made, which is 30 degrees. So we do 4 cos 30. You put that into a calculator. What'd you get? In decimals? 3.5 Webers. And that's the end of 7.5.3.